So far, all we've been talking about are semiconductor junctions. So we have talked about PN junctions in which we have a P-type material and N-type material together. And we have talked about how the semiconductor materials work on either side of the barrier. However, sometimes we can also create devices and put different types of material on each side of the junction. So one of the most common things that occurs, and this is going to lead us into the discussion of MOSFETs. So this is kind of a beginning to understanding how MOSFETs work. But a metal semiconductor contact is something that is quite common and usually is composed of a metal and some type of N-type semiconductor. And why it's N-type just has to do with the Fermi level, and we only have that one type of semiconductor. So it's going to be different because technically there are no minority carriers in this particular situation, as you'll see as we go on. So first of all, we're going to look at a metal on the left and a semiconductor on the right that are not connected. So these are energy levels for a metal that has a Fermi energy on the left and pretty much nothing else at this moment, and the usual construction of energy levels on the right that we've been using all semester. At the top is what we call a vacuum level, and that's just a reference so that we can compare work functions. We talked about work functions on and off throughout the semester, but basically a work function just tells how much energy is needed to remove an electron from the surface of a material. So there's all kinds of different work functions, and at this point we're interested in two things. We're interested in the work function of the metal, which is the distance from the Fermi energy and the vacuum level on the left side, and then the Fermi energy of the semiconductor to the vacuum level on the other side would be the work function of the semiconductor. So we have those two things, and as you'll notice, the work function of the metal is bigger than the work function of the semiconductor, and that's going to be important in creating a rectifying barrier. So we're going to move on and look at also one other parameter that we can look at because we need to know some of these values, and right now we don't know where to get them yet. So the other thing we need to look at is something called the electron affinity. The electron affinity, chi, is smaller than the work function of the semiconductor. It's just the distance between the conduction energy and the vacuum level. So that's also a value where the work function of the metal needs to be greater than the electron affinity, which kind of makes sense. The electron affinity just tells us the energy change when we add an electron. So what the value is just depends on the material of the semiconductor. Now, the interesting thing is that, for the most part, work functions of metals and electron affinities of semiconductors are constants. So we have a table for that. There's a table on D2L, along with your other test 3 materials. So there is a table where you can look up the work function of the metal and you can look up the electron affinity of the semiconductor. The Schottky barrier, which is basically the difference between the conduction energy on the semiconductor side and the Fermi energy on the metal side, is just the difference between the work function of the metal and the electron affinity of the semiconductor. This will be important. That value, the Schottky barrier, is basically an energy barrier that electrons on the metal side need to cross. So this is a value given in volts, just like the other values we get for work functions. So this will be a barrier that will prevent electrons from going from the metal to the semiconductor. Metals all have different work functions. You can see a number of them. Those are all given to you as a table. And electron affinities are similar. We're given those. And the work function of an N-type semiconductor we can calculate. we'll talk about that in a minute, but we can actually calculate that. Oh, you already know how to calculate it, actually. You just don't know, but you do. So, if we take two materials and the work function of the metal is greater than the work function of the semiconductor, and we bring the two materials together, the Fermi energy has to be the same throughout the system. So the Fermi energy needs to move. The only way it can move is on the semiconductor side, not on the metal side. The metal side stays the same, so nothing happens there. But as we've seen before, the semiconductor can actually move the conduction and valence energies up and down depending on where the Fermi energy is. So what ends up happening is we get a depletion region once these are put together, because the Fermi level drops on the end semiconductor, so that's going to pull the conduction energy and the valence energy down. And we've got a couple things we can look at. First of all, the barrier voltage is on the side of the Fermi energy, and that we're not going to worry about. That's just the top of the conduction band there to the bottom of the Fermi energy on the metal side, and that will not change. That depends, remember, on the work function of the metal and the electron affinity of the semiconductor. So that is not going to change. That value is going to stay the same once it's been found. On the semiconductor side, we have a little more work to do, because we do need to know what the built-in voltage is, the difference between sort of that top level and how far down the conduction band has moved. And we can see that it's kind of related to the barrier voltage, but we don't know by how much. If we look at the work function it takes to get from the Fermi energy to the conduction energy, that sort of fills in the gap between what makes up the energy difference on the semiconductor side and what makes the energy difference on the metal side, because they will have to be the same. We can calculate phi sub n. We already know how to do that. As shown on this diagram, phi sub n is just the conduction energy minus the Fermi energy. And you have made those calculations before. So we just use VT natural log of the number of donors over the intrinsic value. You've done that plenty of times. So that's not a difficult value to find. Then, since we know the barrier diode voltage, we can find that. We can calculate the built-in voltage now, because the barrier voltage is going to be the same, and we can subtract the work function between the conduction band and the Fermi energy on the semiconductor side, and we get that the built-in voltage is equal to the Fermi barrier minus the work function of the semiconductor. So far, so good. Once we get those values, those are going to go into kind of figuring out how the material is going to work. You'll notice there is a depletion region, and it has a particular width, and we'll talk about that in a minute. We've actually already kind of covered that. But what we want to talk about for a second is what type of carriers are going to be used when we're actually using this device. Well, there's electrons on the metal side, and that has to cross the Schottky barrier. Electrons from the semiconductor side will have to cross the built-in voltage. There are really no holes involved in this process. There are holes on the inside, but there is nothing to entice them to move in any way. They are always going to be way, way below the Fermi energy. They're not going to really have any place to go. So minority carrier transport is not really a thing with this. This is all electrons moving from one place to the other. And you'll notice they would actually move in opposite directions if they were moving. So under zero bias, nothing's moving. There's a depletion region, and there's electrons on one side and electrons on the other side. And for the most part, not always, for the most part, there is no current flowing. So pretty much all the calculations that go into determining everything we want to know about this situation, the zero bias situation or thermal equilibrium, we can just calculate the way we've been calculating. So we went to the Schottky barrier voltage. We talked about that. You can get that from two values that are looked up on a table. So this means there's never any reason to get the Schottky barrier voltage wrong, because you're looking up the work function of the metal on a table, you're looking at the electron affinity from a table, and you are subtracting one from the other and getting a value. So that should not be a problem. The semiconductor work function, again, this is something that you have done already. You have already calculated EC minus EF. This is just a different form, but it's something that is easy for you to do. And then the built-in voltage is going to be easy to find. The depletion region width and the junction capacitance per square centimeter are basically found exactly the same way that we found them on the N side of a PN junction. Since there is no P material, we just assume that the depletion region is pretty much all in the X region. So that's going to depend on the built-in voltage and the donor concentration. So once we get that and the capacitance, those are just found the same way that we found them before with a thermal equilibrium PN junction. So the Schottky barrier potential doesn't change. That stays the same. If we apply voltage, it's not going to change what happens. We kind of know how electrons work and how they move in a semiconductor, but in a Schottky barrier, from the metal to the semiconductor, there's actually a completely different mechanism that causes the electrons to be able to move. So there's two things that come into play, and I'm going to talk about both of them just briefly, but they both kind of combine in a way to determine how the electrons will cross. The more major determination of electrons moving is thermionic emission. So basically, heat gives enough energy to the electrons to hop over the Schottky barrier and flow. There's plenty of electrons there on the metal. There just needs some heat, and then the electrons will flow from the metal to the semiconductor, which creates a semiconductor to metal current. At thermal equilibrium, there's not going to be a whole lot of heat. There will be a little bit, but not much. The other way that electrons can flow through the Schottky barrier is through tunneling. We've talked about tunneling a little bit. This is a probability-based electron flow that happens through something that it's not supposed to be able to go through. And this actually depends on the barrier function, the barrier voltage to the 3/2. And we're not going to talk a whole lot about that particular effect. We're going to mostly talk about the thermionic emission effect and how to calculate how the electrons are moving. So the value of the Schottky barrier potential doesn't change, depending on, if you apply voltage positive or negative, it's not going to change. For the semiconductor, the built-in voltage doesn't change, but any voltage we apply is going to add or subtract to that value, which is going to basically push the Fermi energy up and down depending on what we do. And that's the way a PN junction was working also. It's just that now we have this metal that's fixed on the other side of the junction, and it's not going to change. Only things on the semiconductor side are going to change. So if we reverse bias a Schottky diode, we add a reverse voltage that pushes the Fermi energy down. When it pushes the Fermi energy down, two things do not change. The potential barrier doesn't change, and the work function between the Fermi energy and the conduction energy doesn't change. So since those two values don't change, something has to change, and that would be the distance between the top of the built-in voltage top there and the conduction energy. So the conduction energy is going to have to move down because the Fermi energy is moving down. So the value of voltage that has to be overcome on the semiconductor side is greater, which we knew because that's what happened before when we applied a reverse voltage, and the depletion region width increases. So that's pretty much the same effect that we had with a PN junction. There's a little bit of a difference in reverse current, which we'll talk about in a minute, but for the most part, it's pretty much acting the same way a PN junction would act if we added a reverse voltage. So, under reverse bias, there's a small amount of current flowing from the semiconductor to the metal, which means electrons are going from metal to semiconductor. The semiconductor side can't get any electrons across to the metal side, and there are no holes to conduct anything. So, we're only depending on a current that is coming from electrons from the metal. And this is really, really different than the reverse current in a PN junction diode. This is a completely different kind of current. So, the equation that determines that is only slightly complicated, not terrible, but it's completely different than the equation that would determine, say, the reverse current in a PN junction diode. Completely different dependencies. So, when we look at the reverse current, and we're really looking at current density because we tend to with semiconductors. So if we look at the reverse current density, the reverse current density is equal to something called A star, which I'll talk about in a second, times the temperature squared times the exponential function to the negative E times the barrier voltage divided by KT. And you know that E over KT is just the thermal voltage, so we could figure that out. A star is something known as the Richardson constant of thermionic emission. And it is just constants except for the effective mass of the semiconductor. So it's defined to be 4 pi times the charge of an electron times the effective mass of the electron times Boltzmann's constant squared over Planck's constant cubed. And all of those are constants except for the effective mass of the electron. Note, as a note, that this is in amps per K squared meter squared. So in order to adjust that, to use, if we were able to calculate and use this, we actually have to divide by 10,000 to get amps per K squared, centimeters squared. So that is going to be a value that we're going to have to change just a little bit if we actually want the value to come out related to centimeters. So that is something that we have to pay attention to. There is a lot of dependency in these two equations. First of all, in the current density equation, the work function features prominently and exponentially, and it depends on the metal and semiconductor materials. So that, once you've picked the metal and the semiconductor, that's going to be something that doesn't change. But the temperature will change quite a bit, and the temperature is included twice in two different ways. So there's a great temperature dependence. The Richardson constant of thermionic emission also depends on semiconductor materials. So the reverse current depends on metal and semiconductor materials. The Richardson constant depends on the semiconductor material, and the reverse current depends on temperature. So all of these things go into making up the reverse current that flows from the metal to the semiconductor. We can calculate the values of reverse current density, and it really is different depending on what we use to construct a metal semiconductor barrier. So this is just an example of values that might come up. This is just using 3 different semiconductors combined with tungsten that all have the same doping concentration of 1 times 10 to the 18th per centimeter cubed, and the same temperature. And you can notice that they vary over orders of magnitude. The silicon has the lowest reverse current density, and germanium has the highest, which is actually makes sense because in general germanium has a higher reverse current anyway than silicon. So that kind of makes sense. And remember, this is current density, not current. So there's not that much current going through because the cross-sectional area of one of these junctions is really, really tiny. So once you multiply this by the area, which could be 1 times 10 to the minus 6, you'll end up with a relatively small actual current. So all we need to do to figure out all the different constants that we want for a reverse voltage across a Schottky diode are almost the same as what we saw before. The Schottky barrier voltage, the work function for the semiconductor, and the built-in voltage are all calculated the same. The only difference is, just like with PN junctions, we have to add the reverse voltage to the built-in voltage to find the width of the depletion region and the junction capacitance per square centimeter. And that's really the only difference we need to do. We just need to add that in. So now that we've looked at the thermal equilibrium and the reverse, we got to look at the forward. The reverse current basically is just a few electrons that go from metal to a semiconductor. When we forward bias a Schottky barrier diode, there's actually electrons flowing in both directions. And these are all majority carriers. So there will be current composed of electrons coming from the semiconductor to the metal, and there will be current coming from going from the metal to the semiconductor where electrons are going in that. So there's two different directions for the current to be going. In a PN junction diode, that's a minority carrier device. That's because the forward bias current is made up. Remember, there are majority carriers that go across the depletion region, become minority carriers, and those minority carriers are what are actually creating the current. In a Schottky diode, the current is only majority carrier electrons. So we don't deal with holes, we just have electrons, and the electrons are all that carry the current. So current density components flowing from metal to semiconductor and semiconductor to metal, but the net current density is in the direction from the metal to the semiconductor. And why would that be? Well, basically because the barrier, the potential barrier for a forward bias Schottky diode doesn't change. So the electrons flowing from the metal to the semiconductor are not going to change that much whether it's a forward or reverse bias. And that gives you current from the semiconductor to the metal. So it is a little backwards when you think about it, but just think about the fact that the semiconductor side changes and provides either more or less electrons depending on the biasing, and those electrons are going to increase or decrease the amount of current directly. So if we forward bias the Schottky diode, we add a voltage, V sub A, that pushes the Fermi energy up. So then the barrier voltage is on the semiconductor side is actually going to be reduced. Remember that the work function of the semiconductor is not going to change. The Fermi energy is going to be the same distance from the conduction energy. The potential barrier doesn't change, so that all of that's going to stay the same. So again, the only things that can change are the potential barrier on the semiconductor side and the depletion region width. So both of those are going to be the things that give when we apply forward and reverse voltage. The metal side is stable like a metal. So when we have current flowing, we have electrons on the metal side, and they're flowing to the semiconductor, the ones that can make it across the barrier, and that gives us a current density in the other direction. So that's the metal to semiconductor current density. The electrons on the semiconductor side are also going through the barrier, and they are creating a current density in the opposite direction. And the total current is just going to be the semiconductor to metal current density minus the metal to semiconductor current density. The cool thing is the reverse saturation current density looked really, really different between PN junctions and Schottky barrier diodes. It's like totally, totally different. But the total current density is almost exactly the same, because what's giving you the driving current is all of what's happening on the semiconductor side. So the reverse saturation current density is related to what's going on the metal side, but on the semiconductor side, we get the actual values that we're used to. So the current density is just the reverse saturation current density, which again is complicated and depends on the metal and the temperature and all that. And then we just use the exponential function times the voltage across the Schottky diode divided by the thermal voltage minus 1. And that's almost exactly like the equation that we used for the PN junction diode. It's a very, very similar setup. So the setup is the same, it's just that the numbers that go into it are just a little bit different. So, some differences between the PN junction diodes and Schottky diodes. Schottky diodes don't require as much voltage to turn on, usually 0.2 to 0.3 volts. Silicon needs 0.7 to gallium arsenide can use up to a volt. Germanium is the only one that is comparable with a forward voltage of about 0.3, but as we've talked about earlier, germanium is not always the best material to use for a diode. It's expensive and difficult to find, so a Schottky diode would be better for a situation where you wanted a low turn-on voltage. The magnitude of the reverse current density is much larger for Schottky diodes, which means the magnitude of the reverse current is larger. And that's actually also true for germanium diodes. They have a larger reverse current as well. But in general, the magnitude of the reverse current is larger. The switching speed, and this is one of the biggest advantages of Schottky diodes, is really, really fast, going between on and off. And the reason is because in Schottky diodes, basically it's like turning off a switch. You're just basically cutting off the flow of electrons. In a PN junction, there's minority carriers stored in the junction. So even if you turn it off, there's still minority carriers that go through. And so it takes a little longer to clear the minority carriers out of the junction and actually turn the diode off if it's a PN junction diode. So turning on and off is faster in a Schottky diode. Schottky diodes, and this is just a definition more than an advantage or disadvantage, but Schottky diodes are something we call a unipolar device. So there's one type of charge carrier. PN junctions are a bipolar device, which means there's two types. There's electrons and holes. So that's not necessarily an advantage or a disadvantage. It just is a truth that if you've ever heard of a unipolar or a bipolar device, that's the difference. One has one type of charge carrier, one has two. So that's one thing you can do, putting together a metal and a semiconductor. But what happens if we turn things around a little bit? We can make out of a semiconductor and a metal something called an ohmic contact, and that's just a linear low resistance junction, and it will allow current to flow in both ways. So if we look at this energy diagram, you'll notice that this time the work function of the semiconductor is greater than the work function of the metal. Remember before when we made the Schottky barrier diode, we had the work function of the metal was greater than the work function of the semiconductor. So if we put these together, now the Fermi level is on the semiconductor side is going to have to move up to equal the Fermi level on the side of the metal, which can't change. So when we do that, we actually find that if we apply a positive voltage to either side of this, electrons will cross. You can see that there's not a great barrier on the Fermi side. There's not a great barrier, and actually the conduction band is above where the metal is. So this is what we call an ideal non-rectifying barrier. There are some details about this that have to do with small changes in work function and non-ideal rectifying barriers, which I am not going to go through. So this is ideal. There are a few differences between an ideal rectifying barrier and an ideal non-rectifying barrier and a non-ideal non-rectifying barrier, but we're not going to talk about them here. It's a little bit theoretical and not really so useful. So another thing that can be done is we can actually create a situation in which the N side is really, really heavily doped, which is going to mean that the work function on the semiconductor side is going to be really, really, really small. And when we do that, they will not be equal anymore because the work function on the Fermi side, or the work function on the metal side is going to be determined by those values that go into making the metal and the semiconductor. But the value of the work function, or the distance between the Fermi energy and the conduction energy on the semiconductor side, could be made different. And what can be done is, if the metal is combined with a heavily doped N-type semiconductor, the space charge width is really, really, really narrow. And that means that electrons can actually tunnel through in both directions. They won't always. Remember that tunneling is a probability-based activity. So this is not a yes, they will do it, no, they will not. It's just there is an increased chance that electrons will tunnel through. And what happens is, if we apply a voltage to either side of this construction, electrons flow really, really easily. So if we apply a positive voltage to the metal side, everything moves up on the semiconductor side, and electrons, it's almost like a ski slope. They just go downhill and they go right over to the metal side. If we apply a positive voltage to the semiconductor side, it's like a ski jump a little bit, but they still get over that barrier. It's very small, and they're able to flow freely. So this is a type of metal semiconductor junction that actually allows current to flow in both directions. So the bottom line is, if the work function of the metal is greater than the work function of the semiconductor, you get a diode, or a rectifying junction. If the work function of the semiconductor is greater than the work function of the metal, you get an ohmic contact that allows current to flow in either direction.